All right, let's get started. Thanks for those who jumped online tonight, and for those who are hopefully watching the recording at a later time, that's all good too. A couple of quick announcements before we get to the meetups. Oh shoot. Um, kind of couple. First one is the New York R conference was announced. It's going to be May 8th and 9th, which is a Friday and Saturday. I've been to 3 or 4 of them. I think this is the 6th year. I can't remember if I missed one or two. Always really good. It's single track stuff. Some good stuff for those who are interested in dabbling in Bayesian. Andrew Gelman usually gives a talk, and which is always entertaining. But always a great conference, good group of people. Anyways, I'll be going this year. I registered. Anyways, here's the link, and I got an email that had a discount code, so I put it in here. If anybody's interested, it's not terribly expensive. Since you all have edu email addresses, you qualify for the academic pricing, which I think was like $280 for the 2 days. I also wanted to alert you to 2 posts that I put on the course website. One, I'm just going to show real quick because I think as you're starting the new lab on the Kobe streaks, it's been using this lab for a long time. It's kind of weird this semester, but uh, if when you start knitting and you start writing answers, because we're going to start doing some simulations, and this will be true for couple of other labs as we go through the course, you may note that the answers may be different as you knit it each time, and that's because of how R and computers more generally do random numbers. It actually turns out that computers are actually remarkably bad at doing random numbers, and so there's over the years, researchers have developed various algorithms to simulate randomness, but it's always deterministic. So I give an example here where I'm just going to do, I'm using the random normal distribution. So I just want one value from the random normal distribution because I didn't specify parameters. This would have a mean of 0 and a standard deviation of 1. This is a function we're going to use quite a lot coming up. And you can see I ask for a random number, I get 0.17. I ask for a random number again, and I get 0.312. Now, what happens is the way these algorithms work is you have some input number referred to as a seed, and then from that seed it goes through a whole process, and on the other end you get something that seems like a random number. In R, you can set the seed. So this is done a lot, especially if you're doing simulation studies, in order to make your analysis reproducible. So if you want in the R Markdown files, if you do somewhere at the top, just set seed and just pick any number. I picked 2112 just because it's Rush's fourth album and just really fantastic. I'm a huge Rush fan. And so here, if I do that, if I set the seed and then call random normal, I get 0.92. And if I come back and do it again, I get the same answer, right? So that's the goal. That's the point. So that it's only random insofar as the seed being random. Um, I'm pretty sure the way R works is it sets the seed when you start up the R session using the current time in milliseconds, and then everything there just kind of goes off of that. Just to show that this is, so you see if I set the seed to another, I just increment it by 1, I get a different number, right? And so the last thing I want to show is here I just have this little loop where I'm just sampling numbers between 1 and 100 here. So I was just doing samples, something a little bit different. But all I'm doing is incrementing the seed each time I go through, and then I'm plotting it, right? And so this is what it looks like. So the x-axis here is the seed, and the y-axis is the random number I got here, limited to 1, between 1 and 100. And what's good here is this is noise, right? This is what we want. Anyway, so I just wanted to just take a brief moment to kind of explain how that works. And if you want to ensure your each time you knit, you get the same answer, you can just put a set seed somewhere at the top of your document. I also added a little thing on colors, just links, for example. And then I think I made reference to a few of these resources before on data visualizations last week. Um, but I would be, when you're choosing colors to use in your plots, there's some interesting links here about using colorblind safe palettes. And if you haven't discovered this color brewer, I use this website a lot to pick my color palettes because I can, pick the number of groups I have, if I want it to be sequential, diverging, or qualitative. And then you have options. So I can say I want it to be a color safe, colorblind safe palette, which might be hard with four groups. I mean, five, but if I go to four, there's one. Um, or, I want it to be photocopy safe. Some of them won't have it, or printer friendly, right? Some of these lighter hues wouldn't print very well. Anyways, so you can go through and you can just get the hex codes. And so in ggplot, there's a scale, or whatever color manual that would allow you to do that. Or there's actually a color brewer set of functions in ggplot that will let you just pick the palette and whether you want it sequential or not. So, anyways, just a couple of little resources there for you to look at. All right, we got three presentations. We'll start with Christian. Just get a notification.
Hey guys, how's everyone doing?
I'm doing well. I can see your screen and I can hear your voice. So the floor is yours.
All right, perfect. Um, so I picked this exercise on the first day, and it looked like an exciting exercise, and I was hoping there was an exciting data set behind it. But when I actually came to do the exercise, there's not a data set behind it. So this is going to be not as exciting as I had hoped, but it's still interesting, I think. So the problem that I picked is exercise 2.1, and it's about mammal lifespans. So I'll just kind of give you a brief overview of the exercise, and then I'll kind of jump into my answers. But essentially, it's talking about data that's collected on lifespans in years and gestation lengths in days for different mammals. And then it just gives you this scatter plot to kind of look at. And then it asks three questions. So it asks what type of association is apparent between lifespan and gestation? What type of association would you expect to see if these two axes were flipped? And then it asks the third question, is lifespan and length of gestation independent, and explain your reasoning. So for the first question, I just essentially said there is an apparent positive association between lifespan and length of gestation. I wouldn't say it's an incredibly strong association, but you can see this picture is a little bit small, but I tried to draw this kind of red line here. You can kind of see there is an association between these two variables. And then for the second one, that was the question about what would happen if the axes flipped, and the association would still be positive. I mean, even if you flip the axes, the fact that the length of gestation tends to increase as lifespan increases, that doesn't change if you flip the axes. And then the third question, again, is are lifespan and length of gestation independent? I said they're not independent, and I took this quote from the book from Open Intro Statistics. It says, two variables are independent if there is no evident relationship between the two. And so, I kind of showed up here in A that there is at least a moderate positive association between these two variables. And if there was no association between these two variables, our graph would look more something like this, where there's really, you can tell there's no association. So,
Thank you very much, Christian.
yep.
Next up, is it Umas? Am I saying? I'm sorry if I butchered your name. Are you there? I see you're listed. See, I think I can unmute you. Oh, but no microphone. Are you there? No, we can. Let's try Ken. Ken, are you there? Did I pick the right Ken? Yeah. Oh boy. Oh, here comes Ken's screen. I can see your screen, but I can't hear your voice. Let me see. I can unmute you on this side, but no green microphone. Oh,
Can you
not.
hear me?
Oh, is that Ken? Who's speaking? Oh, no.
There.
Ken?
Hello, this is Umays.
Oh, Amis. Okay, I can hear Amis now, but I have Ken's screen up. So can you hold on 1 second? Let's just see. Let's give Ken a second to see if his audio comes through. No. No. All right. We'll go back to
Hello.
Amis. All right. Let's see. I'm going to try. Oh, Ken says he's on his phone. Oh boy. Um. Oh boy. This is. Who? Ken or you mas? Um. Who can speak, and then I'll send a. Oh, now I see your screen.
Hello, this is Umays.
Yes. Go ahead. Oh, there's a bad echo.
Okay, hold on 1 second.
Are you there? All right. What about Ken? Did you come back? Oh boy. Can you hear any? All right. Leo, are you there?
We'll go back.
Okay.
Hello?
Let's give Leo a shot. Um.
Oh boy.
Did you get? Okay. Here we
Hello,
go.
Professor, can you hear me?
Yep. Is this who's speaking now?
This is Leo.
Okay, Leo, you go ahead because I can see your screen and I can hear your voice, and
Yeah,
then we'll
this is
swing
Umays. Can
back
you hear me?
around.
Cool. I'll make it quick. So I also chose this
Yeah,
on the first
can you hear
day.
me?
Yes, I could hear you.
Yeah, we can hear you, Mas,
Uh,
but just hold on a minute. I'll have you try to go next.
Okay.
okay, so this
Um,
question,
yeah, so
No.
my name is Umays Siddiqui,
Yeah,
and
Umesh?
one thing I
You
actually
must not
wanted
be
to
hearing me.
mention before I begin is that
Oh, yeah,
Hey,
Umesh?
I posed a link
Yeah,
Mas,
to the presentation.
you know what? I can
Uh,
mute him.
uh,
Go ahead,
okay.
Leo, and I'll text him.
Okay.
All right.
So the question I picked was actually really simple. It's just a bunch of numbers, and we're shown the statistical summary of each of the quartiles, and the question is to just create a box plot of the distribution of these scores. Um, so that was a bit easy, and I didn't know how to fill 5 minutes, so I did more of the calculations manually. First, it's the inner quartile range, which is the third quartile minus the first quartile. It's the space in between the boxes, which is 82.5 minus 72.5, and that's 10. And then we need to find the length of the whiskers, which is 1.5 times the inner quartile range, which is 15. So the top range is 97.5, but the max value is 94. So I put this together here to find the max value within the whisker range, which is 94. And then did something similar for the bottom, since the initial whisker bottom is 57.5, but that value is not there. So we have to find the next value that's within that range, which is 66. So we did a box plot of the scores, and this is the box plot. That's top of the whisker, bottom of the whisker, one outlier. I also did it with ggplot, which is essentially the same thing. And one more, I did it with ggplot, but then I put horizontal lines for the whisker top and whisker bottom that we calculated. That's it.
Nice. Thanks for including the ggplots. That's great. Just by point of clarification, presentations really meant to be no more than 5 minutes, so don't worry if it's less than 5 minutes.
Oh, okay.
All right. So, okay. So you know what, Ken? Since Ken dialed in, let me make you presenter. Oh, I'm gonna go with Ken first because I think he's ready. Moss, maybe try calling in if you're trying. If you're on Wi-Fi, sometimes the latency can become a problem. And all right, Ken, I can see your screen. Can I hear your voice? I can't hear your voice. Which is strange because I see a green microphone. No, um, are you sure you picked? You said you called in. I can't hear you. Yeah, nothing's coming in. Wow. All right. And then we're getting to about the time where I'd like to move on. Moss, can you hear me? Oh boy. All right. Oh, Moss, I think you're going because I can hear myself through your. All right. You know, I don't want to spend much more time. So Moss and Ken, you can message me if you want to try to record these and post them, or we'll just give it a try next week. um, ping me and maybe we can just take a couple of minutes and just try it before next week. It's unusual that I have this much issue and I can't find myself, and now I'm a little flustered. I'm sorry. All right, let me get back to my slide deck. Here we go. Huh. I wonder. Good. Well, all right. So yeah, tonight we're going to talk about probability, and I'm really going to focus very much on the high level stuff here. Not, I know probability is in the name of this course, and we're going to kind of, this will come up really quite a lot as we go through the next few chapters in a different way. So tonight's really just about laying out the definitions and foundation for the language that we're going to use. So as we start talking about distributions and other types of things, that we kind of have this common language. I'm also kind of working on the presumption that what's in this chapter 3, it should be largely review. And so anyways, that's just a little bit of background for what tonight is. It may um, it may feel somewhat incomplete, and I think that's in part because this is just the beginning. So when we're talking about what are the key properties of a probability model, and the first one is we're usually talking about the probability of some event A, and we kind of represent this as P of A with P and A in parentheses. So A is the event, and P is just saying it's the probability of some event. But what's really key about probabilities, and as we work through these and as we define probability distributions, is that they have to range between 0 and 1, where 0 means that the probability of that event is impossible. It's never going to happen. And if you have a probability of 1, that means it's always going to occur. The majority of what we're going to do this semester is presenting probability models from the frequentist point of view. And that's the probability of an outcome if the proportion of times the outcome would occur if we could observe it a random number of times or an infinite number of times. Whereas the Bayesian interprets probability as a subjective degree of belief. That is to say, for some event, two separate people could have different viewpoints and so assign different probabilities. And often the Bayesians view the data sort of as truth, and so we can build probability models around what we are actually seeing. And so how you construct those, and there could be slight variations in how you construct that, would result in generally slightly different interpretations. Where this frequentist approach, we're going to learn some properties, under the assumption that we could do things an infinite number of times. And I'm going to show these largely through simulations. Now that we have fast computers and are available, we can do that. So we'll probably largely do it from the frequency point of view, and then hopefully when you start to switch to the Bayesian point of view, having that background, will make it a little bit easier, and then hopefully we'll also reinforce those points of view. And there's been some conversations both individually and as a group in the Slack, and I like this to keep coming. I don't know if I really ascribe to one point of view or the other. I tend to be more pragmatic about it, and there are certain situations where certain modeling techniques are going to be better, and sometimes the Bayesian approach is going to be better, and sometimes the frequentist approach is going to be better. It's to think each method is inherently good or bad, but each can be abused in different ways, and they often are. So a lot of what we're talking about, and especially from the frequentist point of view, but I think this applies more broadly, is this notion of the law of large numbers. And so what we're saying here is, the more observations that are collected, the proportion of currents that we're observing. So if we observe some probability, if we have more and more data, it's going to converge to some outcome, or the true probability in the population, or if it's an infinite. In some ways, if you've taken calculus, it's this notion of limits, right? Where as you take the limit, as something approaches infinity, it kind of it settles into a fixed value, right? So here's a concrete example. You get the coin toss. If um, when if the heads comes up on each of the first 10 tosses, what do you think the chance of another head coming up on the next toss? Is it 0.5, less than 0.5, or greater than 0.5? Well, in this case, because each event is independent, each event has the same probability, 0.5. But so there's still a 50-50 chance. So there's not the probability doesn't have this thing that things are due. And so this is often referred to as a gambler's fallacy, because we kind of have this intuition often about this sense of the law of large numbers, that we should get the same amount of heads and tails, but each event in and of itself is independent, and so you need to be really careful about that. So I have this little shiny app that's in the Data 606 package, and this is what it looks like, and you can kind of see here what I'm doing is simulating, in this particular example, 100 coin tosses, the way you can think about it. So I have a couple of sliders you can play with. The first one is the number of games, and I have the odds of winning. So I start at 1 out of 2. So you can think of this as a coin toss. If I get, say, heads, I add 1. If I get tails, I lose 1. And here I'm just doing one run, and I could do this. So you could see the average after 100 games is -4 is the way to think about this. I lost 4. But I could do another one, and this one here, I happen to come up 4, up 16, -16. But to think about this notion, right? And so we're always ending up relatively close to to 0. And we can see if I just do 20 at a time, right, it kind of looks symmetrical over there, right? So that's that sense of the kind of starting to get a sense of that law of large numbers, where getting half as many heads and tails is equal. Now, of course, if I change the odds, let's go to 1 and 6. So that would be like, I win if I get a 1 on a dice roll and lose otherwise. Where are you going to end up? And so here I do 100 games, and I end up at -16, -72, right? And I could do a whole bunch. You can kind of sense, right, and sort of hopefully intuitively you recognize I shouldn't end at 0 because the probability of winning is now 50-50. It's now 1 out of 6. All right. So so let's look at, so here I just pulled out one example. So here I'm so you can kind of see how the Shiny app works a little bit. So I'm just randomly sampling from -1 and 1. In this case, I'm doing 1,000 times with replacement, of course, because otherwise I would run out after 2. And then I'm just taking the cumulative sum of this vector. So this, I'm going to get this vector coins, which has a length 1,000, taking the cumulative sum and then plotting it, right? And we see it looks like there's a lot of noise. And if I look at this plot this way, right, one might conclude that, wow, geez, I ended up pretty far away from 0 up at 30. But what I want you to consider here is, what is the range of possible values here, right? So if I got heads 1,000 times, then I could have ended up at a positive 1,000. If I got tails 1,000 times, then I could have ended up at negative 1,000. So the range of possible outcomes I could get here is is 2,000 is the range, right? Somewhere between negative 1,000 and 1,000. Right? And we can kind of get a sense, if I just rescale the y-axis to what it could possibly be, we see that it looks fairly flat and actually is pretty close to 0. So scale kind of matters a lot here. So in this one example, we're gonna end up still pretty close to 0. And what we're gonna start building on next week is I'm gonna come back to this model and say, well, what happens when I end here, right? In this case, where I had 20, what's the average of these 20 ending points? And that's gonna show up next week as we start building up some different distributions. All right, a couple more definitions. We have disjoint or mutually exclusive outcomes, and those are merely outcomes that can't happen at the same time. This is going to be an important thing to consider when we start testing the assumptions of a lot of our models. So in the case of a coin toss, right, that's disjoint, has a disjoint outcome or distribution because you can't have heads and tails at the same time. Not considering the case that maybe you can land the coin on its edge. Right, a single card drawn from a deck cannot be an ace and a queen. Non-disjointed outcomes means they can that they can occur at the same time. So you can get an A both in statistics and econ in the same semester, right? You can get an A in 606 and 607. So we start putting these things together, and if we think about probability distribution, so the distributions are really just going to be a collection of all the outcomes, or a particular probability distribution. So if we think about gender as assigned at birth here, typically it's dichotomized. So I'm thinking this is more like sex than gender. Don't mean to be non-inclusive. You can think of this heads or tails. So the rules for probability distribution is all the events must be disjoint. The probabilities of each event must be between 0 and 1, and then the sum of the probabilities must equal 1. So we've accounted for all the different combinations. We could look at the distribution for two children. You could think of this as you have 2 kids. You could have a male, female, male, female, or then a female, male. Right, and the outcome of each of those could be 25%. Right, and so because each one is between 0 and 1, the sum of all of them is 1. So this would be a full probability distribution. We also have this notion of independence. So 2 processes are independent if knowing the outcome of one provides no useful information about the outcome of another. So knowing that a coin landed on the head of the first does not provide any useful information on determining the second. Knowing the first card drawn from a deck is an ace does provide useful information, right? So if you think about blackjack, and there was, I think, a movie and a book called 21. There were students from MIT that went to Vegas and did something called counting cards. And the way counting cards works is that each time a card is played, you're actually changing the probability in the next event by knowing the outcome. So if you can keep track of that, then you know at certain times of the game, certain cards are more likely to come out. And so if you can bet on that card coming out, um, then those odds are changing, right? So nowadays, I think most Vegas casinos use lots of decks of cards, so that the change in that probability is very small, and doesn't really matter. We're going to come back to this notion of independence in a couple different ways, because um, I find it seems like when we think about it in terms of coins and decks of cards, it's pretty straightforward. But there's some situations that get a little bit a little bit weird, where we may be violating this independence assumption, and may not recognize it, right? Um, so and technically, when you do random samples, right, depending on how many people you randomly select, you select some, the odds of being selected in the next one is actually changing, right? Um, if you even think about like these polls that are going on in, for, the elections going on, the probability of being randomly selected is maybe 1 in 300 million, right? If there's 300, assuming there's 300 million Americans, once somebody's been selected, my chances of being selected as the second person is a little bit greater. It's 1 in 299, 2999, whatever, right? But that change is so small to say that they're independent. But when you start sampling from smaller groups, that can become an issue. I also have questions that I've been thinking about, and I'm going to pose this, and we can, if people are interested in discussing a little further in the Slack channel over the next few days, I'd be happy to. Just having a conversation in education where, when we often do studies of, interventions, and we sample, um, again, males and females in classrooms, and we presume that the outcome, between students is independent, but we often know that there are certain phenomena, in particular, something called a stereotype threat effect, where there's quite a bit of research that suggests that, like, girls in particular do better in mathematics classes where they're in the same gender class than a mixed gender class. And that's in part, so there's it could be the same students, right? And that's the stereotype threat effect. So the presence of some other gender can do it. There's similar impacts of Asian Americans, or in classrooms, tend to perform greater than maybe their non-Asian student counterparts, right? Where if you separate them out, those differences diminish, right? So that's a stereotype threat effect. But that has an implication on independence that was alluded to in the presentation earlier, right? There can be these relationships that we start to discover, and that can have an impact on how we build up these probability models, and how we might want to do some random sampling, or some other procedures to kind of understand this. So we have some ways of checking for this. So if the probability of A occurs given that B is true, which we're going to do the shorthand, we're going to use this vertical line here, the pipe operator. If you're have a Unix background, right, the probability of A given B is how this is read, right? So if the probability of A given B is equal to the probability of A, then the probability of A and B are independent. And so I think it's easier to look at this through an example. So if we have, say, the probability, I'm missing, did I jump over? Okay. So I'm missing a word here. It should be the probability that guns protect citizens, right, is 0.58. So you can think of this as like a survey question. You polled a bunch of people, and 58% said think guns protect citizens. But then from new North Carolina residents, say gun protects ownership, given that the resident is white, right? So we're saying protect citizens given that the respondent is white is 0.67. If you're black, it's 0.28. If you're Hispanic, 0.64. So the fact that the probability varies across race and ethnicity here, is indication that these are non-independent variables, right? And that may have some implications in some of our statistical models going forward. So I need to stop that other Shiny app and start another one. Just give me 20 seconds here for this to start up. Oh boy. Try it again. So this is another way of doing probability models. And this is actually a little shiny app I developed years ago for a student who was in psychology who was interested in developing interventions for people who have, an addiction to gambling. And so the idea here is this is actual real data. This is a table here. So in New York State, these are scratch-off tickets. And these are the odds. So you can go to the lottery website and you can get the odds because they have to publish them. So the way you read this is for to win $1, the odds are 1 in 15. The odds of winning $2 is 1 in 11. I don't know why winning $2 is more likely than $1, but that's how this this is how these tickets were set up, right? All the way up to a $2,500 ticket, which is 1 in 618,000. So this value is simply the winning, just as a numerical value, because I'm going to use that kind of behind the scenes. And so what this little app does, it's very simple. You can decide how long you want to play, or how many tickets you want to buy. I start at 365, figuring the notion here is I'm going to buy one scratch off ticket a day for a year. How much would I win or lose over a year? And so I'm simply doing 365 using these odds, always subtracting $1 because it costs $1 to play the ticket, and then adding up. So you can see every bump up or each dot here. So in this case, I won $20. Looks like maybe twice in the year. Otherwise, I had a pretty long streak here in losing. And so, this is something you could give, somebody, a gambler, and say, okay, well, let's do another year. And it leaves a little shadow so you can see that first year I did, and I could do this over and over, right? And so here's the first time I'm kind of positive. I want $100 here, right? And you go through and there's actually a button so I can do 10 years at a time. Oh, it finally happened. This has been a few semesters when I had one that was actually really positive. But I can keep doing this and you can kind of get I got another one. Wow, twice. Maybe as extra credit, somebody can calculate the odds of doing that if I have about 100 of these a semester. So anyways, so you can go through here and get a sense, right? And so what we're going to start focusing in on is this n value, right? Because what we're also interested in is expected values. But let me digress just from that for a moment to talk about what, so we're talking about here are random variables, right? So you can think of these outcomes as random variables at the end of a probability, right? So these are whose value depends on some outcome of a random event, right? So the outcome after 365 lottery tickets, right? And we can do that lots of times. We tend to use a capital letter like X to denote the random variable, and the values of the random value by a lowercase x, right? So we're now saying probability of X, capital X equals little x. So there are two types of random variables. We have discrete random variables, which are usually take on integer values. So number of credit hours, number of this term versus last term. Or we could have continuous random variables, which take on real values. So the cost of books, different, or the difference in the cost of books between this term and last term. I would consider the lottery tickets are probably discrete random because they're in dollar increments. So from there, right, what we want to get to is this notion of the expected value, right? If I buy 365 lottery tickets a year, how much am I expected to win or lose, right? And so that's the outcome of some random variable over time. It's also, we can think of it as a measure of center. So it's a type of mean that we've already talked about. So here it is, the sum, the sum of the outcome times the probability of that outcome, right? So looking at, so let's look at a simpler example, and then we'll return to our lottery tickets, right? So here's a silly little game where you win $1 if you get a heart, $5 if you draw an ace, including the ace of hearts, $10 if you draw the king of spades and nothing for any other card you draw. So first thing we want to do is write out our probability model, right? So, we kind of have rows here. So we have heart, ace, king of spades, and all else. We know, right, from the game, the X here, this column is going to represent our winnings, if you will, or the value that we get for that outcome. So we have 1, 5, and 5, 10, and 0. And now we gotta kind of figure out some of the probability. So the probability of getting a heart, not an ace. So there's 13 of each. Man, it just complete, type of card. I'm trying to remember what it's called. Somebody will throw it in the chat. Suit. Thank you, Jeff. I do not gamble, so and I don't play cards. So, is 12 out of 52 because there's 52 cards in a deck, right? To get an ace is 4 out of 52. So that king of spades is 1 out of 52. And then if you just do a little bit of arithmetic, we have 35 cards left. So the expected value here, right? Think about what we're going to do here is we're going to take the product of each of those, the value times the probability, and then sum it, right? So here we can do 1252 times 1, 5 times 4 52nd, 10 times 1 52nd, and then 0 times that. Add that all up, we get 0.81. So in other words, if we were to play this game, we would expect to win 81 cents over the long haul. So that's the expected value. But then the question is, all right. So here's what the probability distribution looks like. It's the probability of each outcome. So you could get 0, you could win 1, 5, or 10, and these other bars here are 0 because those aren't possible outcomes given this scenario. So the question is if this game costs $1, should you play it? And the answer would be no, because then you would take 1 minus that expected value would be your winnings. So you would expect to lose 19 cents on this game, over the long run. So returning to that lottery ticket example, right? So here's the data frame that I showed in the Shiny app. So we have all those values. I'm just doing some renaming and making sure they come in as integers. So there's 2 ways I could approach this. One is through simulations. So it turns out this one we could calculate and because we could specify the whole probability distribution. But simulate, I want to try to give a little bit of an introduction to a simulation. So here, what I'm going to do is sample, right, here I'm doing the max on the odds, right? So this is the max odds. And then I'm going to do, so I'm basically randomly picking a number between 1 and 618,000. So if I actually get 618,000, that number, that's my $2,500 winning. If I get something evenly divisible by this number, then I'm going to get that winning. So I don't know if I talked about this. So I gave another intro to our workshop recently, and I know I didn't either in this class or somewhere else. This is one of those instances where the modulus is really important. So if you did R, you learn about the R operations, right? So we have obviously addition, subtraction, multiplication, division. The 2% sign is something called the modulus, which gives you the remainder. So if I do 3 modulus 2, I get 1, right? So 2 goes into 3 once and there's 1 left over, right? So it's always the remainder. What's kind of handy in this situation are probability models. This is a situation. So what I'm doing is I'm randomly selecting a number. And if that number is evenly divisible by 15, right, that would every 15th number, then I won $1. If it's evenly divisible by 11, I get $2 and so forth and so on. So I'm just going through and for each one of those, I'm just taking the in the situation where I'm in, I have a modulus that's equal to one of these odds, then I'm going to set the value to the of that in that vector to the winning to this column, and subtracting 1 because it costs $1 to play the game. And here I'm just printing out the first 6. So you could see I lost $1 on the first 3, then won $1, and then I broke even, et cetera, et cetera. Right. And so the mean of this vector is, the expected value. So here I expected to lose on a single game 53 cents or so. right? So, and I could run this again and again, right? A bunch of simulations or get more, and that's give me one estimate. This is what the distribution of those outcomes look like from a simulation point of view. But in this case, we could actually calculate it out. So here I can just take the value times the odds, multiply it out, and the actual probability here is I'm expected to lose 38.6 cents per game, right? And so, that's not terrible. 53 cents to that. If I were run the simulation again, I would, get something different. We'll talk about that a little bit more so that we're not just having single values. As we start taking these probability distributions and running this lots and lots of times, then we're going to start getting other types of distributions where we can start providing not just the mean value, but now introducing this notion of spread. And that's kind of what we're going to get to next. So you can see here I ran another simulation. In this case, I got 43 cents. Got a little bit closer. So let me pause here. So these are sort of my highlights from chapter 3 to kind of lay the foundation for what's going to come up in the next next 3 chapters in particular. When we talk about, I think the next chapter is titled "The Foundations for Inference," and then we'll talk about inference for categorical variables and continuous variables. I think in that order. But let me pause to see what questions you have now. No questions. Okay. I mean, we could end early, or Mas and Ken, are you still on? Do you want to try to do your presentation now? Speak up. If I hear your voice, then I'll make the effort to. Yeah. Okay.
I have kind of a question that's not
Hello.
vaguely related.
That's not. Go ahead. Okay. Let me answer the question first. Actually, while you ask the question, Mas, I'm going to send you the request to share your screen. So go ahead. Was that
Yeah,
Christian?
it's Chris. If you
Christopher?
want, yes, if one was going to model like a gambling strategy based on previous results, do you have any like of outcomes that had previously happened? Do you have any like recommendations for like maybe a programming language one would do that in? Is that something you would do with like loops in Python, or is there like a better tool for that?
So if I'm understanding the question, it sounds like what you want to do is include some prior information. So it sounds very Bayesian to me.
Okay.
We will talk about that towards the end of the semester, and I will actually show an example. I don't do a gambling example. The example I use, I actually stole from Rasmuth, who I think is a fantastic teacher of Bayesian methods. I have links already in the Bayesian page. So, I mean, you can do all I do it. What you want. What a lot of people end up doing if you're going to do serious Bayesian work, though, is use Stan. I think is the more common one, but there's R packages to interface with Stan, so you can run it from R. You could do Python for sure, but there's a lot of good tools in R to do it. So I'll show an example. I'm going to let Yumas. Am I saying your name correctly? Can you say it one more time for me?
Yeah, this is Umesh. Can you hear me now?
Mace. It's like a hard day. Yeah,
Hello?
I can hear you. I can see your screen. So go ahead.
Okay. So yeah, my name is Umesh Siddiqui, and I'm going to be presenting problem number 2.15 from the textbook, and it's page number 58 in the PDF version of the textbook. So this problem actually is asking for, for each of the following, state whether you expect the distribution to be symmetric, right skewed, or left skewed. Also specify whether the mean or median would best represent typical observation in the data, and whether the variability of observations would be best represented using the standard deviation or IQR. Explain your reasoning. So there's 3 actually types of data sets that they're asking about what the distribution would be like, and what's the best way to calculate the typical value, and explain the variability. So part A is about number of pets per household. So similar data provided with this problem, I had to make assumptions, and for the number of pets per household, the first assumption I made was very few households will have many pets. Most people will have pets, one or two, and a lot of households, they're not going to have pets at all. So in order to visually kind of get an idea, what I did was I used some simulated sampling of the data, and I used our feature random sample data set of 10,000, and I assigned based on my assumptions, I assigned the various population to these different numbers. 0 means 0 pets, 1, 2, 3, 4, 5, 8. So I just did based on the assumption, and the bar plot that actually shows us that it's going to be more positive scoot, so we see a long tail towards the right, and from the box plot we can see the IQR, which is this section here, and then the median value, and then there's one outlier, and this is all sample data set. This is not real data, so I use that, and we can see that the mean, the best way to describe the data would be using the median, and also to describe the variability in the data we can use the IQR for this part A. Similarly, for distance to work, which is a number of miles between work and
You're breaking up, but I think.
home.
Oh.
I also made.
Oh boy, yeah, I think we lost him. Well, oh, oh,
Lessons here where people will live far away from work. Most people will live close.
All right, I'm gonna cut
their
you.
Work, not more than 5 miles.
Oh, you mice, can you hear me?
That's an assumption I made, and then I generated data set represents those assumptions, and my assumptions, I can see that this is also right scoot, and also over here you can see the mean is higher than the median, and so the typical value would be best represented by median. Hello.
Yep. All right. You're dropping in and out pretty bad. I'm just gonna cut you off because you posted your slide deck. So anybody who wants to see, there'll be a link in my slides to UMass's slides. So if you wanna just follow up on the details, this is great. Not any of your fault. It's the internet is not cooperating tonight. So let me just, so we can start to wrap it up. But I do want to make sure if there are any other questions that they get answered. Does anybody else have any other?
I have a question. It's not about content specifically, but about like your slide deck for these meetings. Where can I find them?
They're on the course website. So if you go to the Meetup page, there they are. So there's a link to the slides in the video.
Right, I remember that. Cool, thank you.
Yep. So usually in the next, so I mean, if anybody wants to, like, a little behind the scenes, when I quit here, GoToMeeting has to convert the video. I don't know why, but that's what it does. Sometimes it takes like 30 minutes. Sometimes it takes an hour and a half. I never know why. It's not correlated to how long the meetup was. And then I have to upload it to YouTube, but at 9:30, I'm usually not up to do that, so I do it in the morning. So, anyways, usually in the morning I'll post it. So can you go over some of the algebraic properties of expected values? Like, I could, but we're not going to do a whole lot with that. But you were asking for a resource earlier, and I forgot to look. I was in my office today and other office, and I forgot to look. So let me write a note. But I can probability book. Any other questions? Yeah. Oh, so the phone. That's interesting. Were you using Wi-Fi calling? I don't know if it's a good thing or a bad thing. If you have an iPhone, I assume Android does the same thing. Oh, I learned my lesson years ago. So I'm like, when I do these meetups, I'm hardwired. I have an Ethernet cable to my computer. I don't rely on Wi-Fi because it's just. Oh well, I have T-Mobile too. I like the price, but I had better service with Verizon. Yeah, if you can hardwire, that's great. Tonight's particularly bad. I don't know what's going on. The other thing you do is you go to speedtest.net and make sure. But with GoToMeeting, it usually adapts to the bandwidth pretty well. But if the ping kind of gives you a good sense of latency, that's usually the bigger problem. Oh, FiOS, rub it in. I wish I had FiOS. So that doesn't make sense. But if you're in New York, I could see Wi-Fi being problematic. So if you only need to pay for GoToMeeting to host meetings, and so I got to figure this out. Actually, I'm using the GoToMeeting account I'm using for this is technically through my role at Excelsior College, and I just learned that they're switching from GoToMeeting to Zoom in March or April. I think I have to April to figure this out, but sadly, I think this is going to happen before the end of the semester, so I don't know what to do. So I use Zoom. I've been using Zoom more, but I know CUNY, this program has been using GoToMeeting, which is fine, but they don't have enough accounts for every instructor to have their own, unfortunately. I may need to follow up on that. Anyways, I I don't know if there's a free version. You shouldn't need to pay for it. Yeah, Zoom seems to be fine. That's what Cornell uses, and it works well. There's a few little quirky things that I don't like the way it auto switches the video when you do video calls. But anyways, any statistical questions or course questions? All right. Well, thank you all for making it to the meetup tonight. I did not realize that this was a day off. I completely missed that on the academic calendar. And to not do this meetup tonight would have really made my life a pain to redo the schedule because I got things to fit in kind of nicely. Because spring break's a little weird this year than other spring semesters. So, anyways, have a good night, everyone, and I'll see you in the Slack channels or next Wednesday. No worries about the technical issues. It happens.